Erosion tests are performed in a walk-in freezer. Three different impurities, ammonium sulfate seen here, are measured and combined with snow to create a mixture that will eventually be mixed with water to freeze into a solid cylinder of ice. Precise measurements are necessary to ensure a ratio of 40% impurity to 60% snow by mass. The impurity and snow are mixed together in a large barrel. The impure snow is mixed little by little with near-freezing distilled water in a large steel drum to create a wet, slushy substance. The mixture is thoroughly stirred to create a homogeneous mixture. This will eventually freeze into one solid block of impure ice. After 48 hours, the surface is abraded slightly in order to remove any top layer of water ice that may have seeped upwards and frozen during the freezing process. In order to reach temperatures similar to those on Titan, 2 tanks of liquid nitrogen are connected to copper piping that enters the freezer and is wrapped several times around the drum that houses the impure ice. The liquid nitrogen is pumped into the copper at a near vapor and runs for approximately 2 hours before the ice reaches its target temperature range of -130 Celsius. A thermocouple frozen directly into the ice cylinder allows monitoring of the temperature of the ice. Once the ice reaches its target temperature range, a clast made of limestone is dropped 500 times from a height of 20 centimeters to simulate impact erosion on the ice surface. Following the drop tests, the ice surface is vacuumed thoroughly to remove any debris or snow left over from the rock drops. A camera and laser are both mounted at a fixed distance on a mobile crank track above the ice. A photograph is taken every 5 millimeters along the ice surface for a total of 107 pictures. photographs are then processed through MATLAB software. The resulting analysis illustrates the change in the elevation of the ice surface occurring after each set of drop tests and subsequent scans. After 20 trials of drop tests and 20 surface scans, the ice is jackhammered out and the drum is prepared for the next batch of impure ice. Small cores of each impure ice are created and broken to measure tensile strength. These break tests are conducted inside an insulated box that is lined with copper piping to allow liquid nitrogen to cool it to Titan temperatures. A large cooler where the ice samples will be chilled and set for breaking has also been lined with copper piping to permit liquid nitrogen cooling. The ice core samples are chilled in the cooler until reaching temperatures similar to Titan. The insulated box sits on a versiloader, a machine that raises the box upwards at a constant speed, measuring the force applied on each ice core until the core eventually fails, breaking in half. The ice cores are set in a steel fixture within the liquid nitrogen cooler. Two small sticks of bamboo are carefully placed on the top and bottom of the ice cylinder, ensuring that the applied force is focused along that axis. Once the ice core is correctly set within the fixture, it is quickly transferred to the insulated testing box. The versiloader is then powered on and begins to slowly raise the entire box and ice core within it. The air temperature of the box is monitored and recorded. The versiloader applies a compressive force to the ice core and measures this force until the ice finally breaks in half vertically in tension. After breaking, the internal temperature of the ice core is measured by placing a thermocouple in between the two halves of the ice core. The metal fixture is removed from the box and the process is repeated for each core of ice. The tensile strength of each core is calculated using the applied force measured by the versiloader along with the dimensions of each individual core.